Okay. So today we will be discussing two problems on power electronics. The first problem, a buck converter feeding a variable resistive load is shown in the figure. The switching frequency of the switch S is 100 kHz and the duty ratio is 0.6. The output voltage V0 is 36 volt. Assume that all the components are ideal and that the output voltage is ripple free. The value of R that will make the inductor current just continuous is. Is the question clear, Saurav? Okay. So, usually we know that when the voltage across inductor is positive, its current will rise. Say this is inductor voltage. If it is a positive value, the current will rise. If it is a negative value, the current will fall. At steady state operation, these two values will be same. The minimum values as well as the maximum values of corresponding cycles will be same at steady state. So in the problem it is given that we have to find the value of resistance which will give a current which is just continuous. So just continuous means what? The current will be just continuous means the minimum value of inductor current will be 0. So if you understand that, now we can proceed. So given it is a buck converter and it is continuous conduction mode, so you know that the output voltage is duty cycle times the input voltage. It is given already. The output voltage is 36 volt, input voltage is 60 volt, and duty ratio is 0.6. And even if duty ratio is not given, also you can find the duty ratio. So here duty ratio is 0.6, input voltage is 60, which will give you 36. So it is already given in the problem. Now let us draw the inductor current. So during the DTS time, the switch will be in the on position. So when switch is on, what is the equivalent circuit? This is the equivalent circuit. The diode will be reverse biased when switch is conducting. So 60 volt and 36 volt is there. So the voltage across inductor VL is 60 minus 36, which is 24 volt. So it is a positive value. So the voltage across inductor VL is 24 volt during DTS duration. Now during 1 minus DTS duration, that is the switch is off. At that time the diode will conduct. It will be forward biased and there will not be the input voltage in the circuit. So diode will be conducting, inductor is there, 36 volt is constant output. So inductor voltage VL now is minus 36 volt because the inductor voltage is plus minus VL is connected opposite to the output terminals. So output voltage is minus 36 volt, so it is a negative value. So now, charge will get stored in the capacitor, but capacitor is mainly provided to maintain the output voltage. How much charge is stored in the capacitor is not our question. Whatever the inductor current is, inductor current will be a rising and then falling. Inductor current will be like that. So the ripple in this inductor current will flow through the capacitor. So the capacitor current will be like this, whose average value will be 0. So because of this current, some charge will be stored in the capacitor in one cycle. That charge will be discharged in the next cycle. You understand? We'll discuss about it after we solve this problem. So the problem asked is what is the value of resistance? So now we got the inductor voltage. So during the switch is conducting, the inductor voltage is 24 volt and the switch is not conducting, the inductor voltage is minus 36 volt. So you understand that when the switch is conducting, the inductor current rises. When the switch is not conducting, the inductor current falls. So in the question it is given that the inductor current is just at the verge of continuous conduction mode. So the minimum value of current is 0. So now another point is inductor current will flow through the load I naught and the capacitor. So this is your inductor current IL. So you know that there are two rules in a DC to DC conductor under steady state. One is inductor volt-second balance. That means the average voltage across inductor will be 0 at steady state. By applying this rule, we will get the relation between the input voltage and output voltage. By applying this relation only, we got output voltage is D times input voltage in the case of buck converter. In the case of boost converter, it will become output voltage is 1 by 1 minus D times input voltage. Both all these relations we get when we apply inductor volt-second balance. Similar analogy applies to capacitor where the average current across a capacitor is 0 under steady state, which is called capacitor charge balance. Okay, so you asked capacitor will store charge. Definitely the capacitor will store charge, but that stored charge it will dissipate in the next cycle. So average capacitor current will be 0. So what is the meaning of this? Whatever current is flowing through the capacitor, its average value is 0. That means capacitor only carries ripple current. So whatever the ripple current, so inductor current is like this. So this can be decomposed into a ripple value whose average value is 0 and an average value. So this is inductor current, out of which the ripples in the inductor current will flow through the capacitor and the average value will go through the load. So this is our load current. So in short, can you tell me what is the average value of inductor current and the output current relation? Can someone explain what is the relation between average value of inductor current in a buck converter and the output current? Okay, they will be equal. As I explained, the inductor current flows through capacitor and the load, where the capacitor only carries ripple current. That means the average current through the capacitor is 0. So whatever the average value is there in the inductor current, that will flow through the load. So the load current is nothing but the average value of inductor current in the case of a buck converter. So in the problem, we know that this is our inductor current IL, whose minimum value is 0 and maximum value is say I peak. What is the average value of this waveform? So we have a waveform in one cycle, it is a triangle waveform. It will repeat. So this whole duration is Ts. This value is I peak. So applying the triangle area under the triangle, the area under this curve is half, base is Ts, height is I peak, the whole divided by the base. This will give you the average value. So average value of inductor current. This is inductor current. So the average value of this inductor current is half times I peak. Now you know that ripple current, peak to peak ripple, let it be delta IL. So delta IL is same as what from the figure? It is same as the peak current. So at the boundary of continuous conduction mode and discontinuous current conduction mode, the peak value of inductor current will be same as the peak to peak ripple of the inductor current. Some textbooks represent the peak this as delta IL. So you have to keep in mind the delta IL which I took is the peak to peak delta IL, peak to peak ripple current. Or in short, the maximum value of inductor current will be same as the peak to peak ripple current at the boundary of CCM and DCM. This is applicable not just for buck converter, this is a universal relation for any type of converter. At the boundary of CCM and DCM, peak value of inductor current will be same as the peak to peak ripple current of inductor. So now let us apply the basic inductor voltage equation. So now you got that the inductor current looks like this, and another relation we got is that the output current is same as the average value of inductor current, which is nothing but half times I peak. This is particular to buck converter. So the output current is half times I peak. Now the output current is same as what? Our load is a resistor and the output voltage is V0. So this current is I0. So what is I0? I0 is V0 by R. So we'll substitute I naught as V naught by R is half times I peak. What we have to find? We have to find R. We know V naught is given in the problem. I peak we have to find. So R is nothing but 2 V naught by I peak. So V naught is already given. I peak we have to find. To find I peak, I will utilize the inductor voltage equation. So now we know that the voltage across inductor during when the switch is on is 24 volt. So we know inductor voltage is L di by dt, where I is the current through the inductor. So rate of change of current through the inductor times the inductance will give you the voltage across inductor. So during dTs duration, you already know VL is 24 volt. And di, what is di? The change in inductor current, which is nothing but 0 to I peak it will change. Or the change in inductor current is I peak minus 0 or I peak, which is nothing but delta IL. Okay, divided by, sorry, DL is this. So VL is, L is already given in the problem, which is 5 millihenry. So VL at the DTS is 24. 24 is 5 millihenry times DL is delta IL, or it is same as I peak at the boundary of CCM and DCM. So this delta IL I replace it with I peak by dt. During what time the change is happening? DTS. So DTS is there. Now D is 0.6 and TS is the switching frequency is given in the problem as 100 kilohertz. So TS is 1 by switching frequency. 1 by 100 kilohertz means 100 into 10 raised to 3. So when you substitute these values, you will get I peak as 28.8 milliampere. So now you got I peak. Now what do you have to find? R. So R is 2 times 36 divided by 28.8 milliampere, which is 10 raised to minus 3, which will come out to be 2500 ohms is the answer. For the students who joined recently, you can go through the problem and ask me if there is any doubt. So in the problem is asked to find the value of resistance where the inductor current is at the boundary of CCM and DCM. So general rule is that when the inductor current is at the brim of CCM and DCM, the value of peak to peak inductor current will be same as the peak value of inductor current. There is a message. Okay. So in the problem, we are asked to find the value of resistance, the value of R. We are asked to find the value of resistance for which the inductor current is at the boundary of CCM and DCM. You know that the inductor current looks like this. It can be, this is a continuous conduction mode. This is the boundary of CCM and discontinuous conduction mode. This is still continuous, but it is at the boundary. Now DCM means the inductor current will become 0 before the DTS period gets over. This happens when the value of resistance is too high. So the current value will be limited. So we are asked to find the value of resistance when the inductor current is like this. So without any given buck boost converters, for every converter, the boundary of CCM and DCM occurs when the peak to peak inductor ripple current, which is this difference, is same as the peak inductor current. So the peak to peak inductor current is always maximum inductor current minus minimum inductor current. When it is at the boundary of CCM and DCM, the minimum inductor current becomes 0. So it will be always the maximum inductor current. This holds true for all converters. Now for buck converter, as seen from the figure, the inductor current gets divided into capacitor current and output current. You have just applied KCL. So similar to inductor volt-second balance, capacitor has a charge balance. So average current through the capacitor will always be 0 under steady state for all converters. So now if this is true, that means the capacitor average current is 0, which means the capacitor only has ripple current. So whatever is the current through the inductor, this current has a ripple component and a average component. So this ripple component will flow through the capacitor and the average component will flow through the output voltage. So whatever average component is there in the inductor current, that average component you will get at the output. So the average value of inductor current is same as output current. So now you will find the average value of inductor current from the inductor current waveform. That inductor current waveform you will obtain by plotting inductor voltage. So when the switch is on, the inductor voltage is positive, so the inductor current rises. When the switch is off, the inductor current becomes negative and the current will fall. So you know the voltage values. You don't know the peak value of inductor current. So you can utilize inductor voltage is equal to L dI by dt equation to get your peak inductor current. Once you get the peak inductor current, you know what is your average output current. Once you know your average output current, your average output voltage is already given. So you can find the value of resistance. So that value of resistance will make the inductor current at the boundary of CCM and DCM. Understood? Okay. We'll move on to the next problem. The separately excited DC motor in the figure below has a rated armature current of 20 ampere and a rated armature voltage of 150 volts. An ideal chopper switching at 5 kHz is used to control the armature voltage. If LA is equal to 0.1 millihenry, RA is 1 ohm, neglecting armature reaction, the duty ratio of the chopper to obtain 50% of the rated torque at the rated speed and the rated field current is. You can go through the problem your own. Okay, so now I'll explain. We are given a DC motor. So you know that a DC motor speed equation. The speed equation is VA by K phi minus T by K phi whole square RA. Is everyone familiar with this equation or should I explain this equation? Can someone respond? Okay. So there are basically two equations for a DC machine which you should remember, regardless whether it is separately excited, self-excited, or any type of DC motor, this series or shunt, this holds true. First equation is the back EMF generated in the machine is proportional to the speed of the machine. The proportionality constant is K phi, which is speed is in, this omega is in radian per second. This is one equation. Another equation is the torque generated in the motor is proportional to the armature current. So it is K phi times IA. The reason I wrote omega, not speed in RPM, is because I need to get same constant of proportionality for both torque and back EMF. So these equations holds true for all machine. Now we have to substitute for these values depending on the type of the machine. For shunt machine and separately excited machine, the K phi, this holds true. But in the case of a series DC motor, you already know your field current is same as armature current. So this K phi is proportional to your field current. So torque becomes proportional to armature current square in the case of a series machine. But regardless, these equations hold true for all DC machines. So you just have to remember these two equations. Just that the back EMF is proportional to the field and speed. The torque is proportional to the field and armature current. So now, for a DC motor, we know that you apply a voltage, there will be a drop in the resistance under steady state I am talking. So this is the back EMF. And this is the current IA and this is the armature resistance RA. Let it be a shunt or separately excited machine. So here you know that your applied voltage is, you apply KVL, IARA plus EB. So V you remain, let it be like that. V is actually armature voltage VA. IA you can replace it with T by K phi, and RA is RA, plus EB is K phi times omega. So now you keep omega here. So omega K phi, I'm taking this to the other side, is equal to VA minus T by K phi into RA. Now you divide all terms by K phi. So your omega is VA by K phi minus T by K phi square RA, which is the equation of speed in the case of a DC machine. Is it clear? This is how you get that equation. I hope it is clear for everyone. Okay. So the speed can be controlled. Mainly we have to control the speed of the machine. It can be controlled in 3 ways. One way is you can vary your armature voltage. Another way is you can vary your field current. That is field excitation you can vary and vary the speed. Another method is with armature resistance. You can vary the armature resistance and control the speed. So in the given problem, they have adopted armature voltage control. They are varying armature voltage to control the speed. That much I hope everyone understood. So now to get a varying armature voltage, they are making use of a DC chopper. A DC chopper is nothing but a DC to DC converter. So you apply a DC voltage, you will get another DC voltage at the output, which is nothing but a buck boost, any kind of converter. So now, if you are proficient in powertronics, you will notice that this is similar to a buck converter. You just observe the previous problem. We have a switch connected to the supply voltage, and we have a diode, and there is the output circuit. So this circuit is nothing but a buck converter. Where you apply a DC voltage, you will get a reduced voltage at the output. And how much the voltage is reduced, it is dependent on the duty ratio of the switch. Is this much clear? Whatever I explained till now is not useful for solving the problem. I just explained what the circuit is. I hope it is clear. So now let us come to the problem. The separately excited DC motor has a rated armature current of 20 ampere. So let the rated conditions, I am representing it as 1. So rated armature current is 20 ampere and rated armature voltage is 150 ampere. Note that armature voltage is the voltage applied across armature. This is armature voltage, not this. This is, let it be V, supply voltage. Armature voltage is what we get at the armature of the machine. So we can draw the equivalent circuit of the machine as armature resistance and back EMF, where this is the armature voltage. Always DC machine analysis is done at steady state condition. So we neglect the effect of armature inductance. We know that under steady state, the voltage across inductor is 0. So there is no drop across this inductor under steady state. So usually we neglect the armature inductance when we analyze a DC machine. So I will draw this properly. So this is our circuit. So from VA I have drawn the circuit. Now under rated condition we have given the rated armature current and rated armature voltage. Now an ideal chopper switching at 5 kHz is used. So the chopper details is chopper switching frequency is 5 kHz. It is used to control the armature voltage. Now you know why we are controlling the armature voltage, because we have to control the speed of the motor. Now if armature inductance, they have given it simply, we won't consider armature inductance for DC machine steady state operation. Resistance is 1 ohm. Neglecting armature reaction, the duty ratio of the chopper to obtain 50% of the rated torque at the rated speed and the rated field current is. So we have a condition here, second condition, where the torque in the case of second condition is 50% of rated torque. So rated torque is 1, subscript is 1. So when the torque if the torque at rated condition is T1, now the condition which we are interested in is half the rated torque. And it is given that the speed in the second condition is same as rated speed and the field under the condition is same as rated condition. So it is given the torque, half the rated torque it is working, but the speed is at rated speed and field current is rated. So this much information we know. Now let us take the two equations which we considered before, where the back EMF is equal to k phi times omega and the torque is k phi times Ia. Now it is given that the speed and field remains unchanged in both the cases. With this information, what can you make out of back EMF in the first case and back EMF in the second case? Joshna, can you tell me? What is the relation between EB1 and EB2? You know EB is proportional to, it is equal to k phi times omega. And another, you know that k phi 1 and k phi 2 is same, omega 1 and omega 2 are same. So what about EB1 and EB2? Saurav, can you tell me?
Equal, ma'am.
Okay, just what?
Equal, ma'am.
Yeah, correct. So EB1 and EB2 are equal. Now, it is given that T2 is 0.5 times T1. So T2 by T1 is 0.5, which is nothing but k phi 2 by k phi 1 multiplied by Ia2 by Ia1. You know k phi 2 and k phi 1 are same. Ia1 you already know as 20 ampere. So what is Ia2? Ia2 is 0.5 times Ia1, which is nothing but 10 ampere. So in the case in which you are interested, you got that you have Va2, you have Ra same as 1 ohm and you have a back EMF. So the back EMF is same as previous case. So this EB2 is same as EB1. This current also you got as 10 ampere. You have to find Va2. The problem asked is you have to find the duty ratio of the chopper. What is the meaning of duty ratio? The output voltage by input voltage. That means at the end they have asked you for D2, which is Va2 by V. Va2 we have to find out V. You know that V is 200 volt. So to find Va2, what you will do? You will apply KVL. Va2 is nothing but EB2 plus Ia2 into Ra, which is 10 into 1. Now what is EB2? EB2 is same as EB1. Now to find EB1, what you will do? You take EB1 circuit. EB1 happens when you apply rated voltage. It is given that the rated armature voltage is 150 volt. So when you apply 150 volt, there is a current flow of 20 ampere through 1 ohm resistance, and this is EB1. So EB1 is nothing but 150 minus 20 times 1, which is nothing but 130 volt. So now you got EB1, hence you got EB2. So so EB2 is same as EB1, which is 130 plus 10, which is 140 volt. So what is your duty ratio? D2 is 140 by 200, which is nothing but 0.7, which is option D. But let us find out the duty ratio in the first case. In the first case, what is the duty ratio? Rated condition. It is nothing but Va1 by V. Va1 is 150, V is 200. So this is 0.75. So when you reduce the duty ratio from 0.75 to 0.7, your torque got reduced to half. Is it clear? Now the answer is 0.7, option D. Is it clear for everyone? Should I explain once again? Joshna, is it clear? Shishir?
Yes, ma'am. Clear, ma'am.
Okay. Shishir? Okay. So that's it. That's for today. Thank you for attending. Meet you tomorrow also. There is a session at 7 p.m. Thank you.